Today, I'm going to demonstrate how to assess the reliability of a PCBA assembly which is mounted inside an enclosure subjected to random vibration environment. For this, we are going to take a printed circuit board assembly card as shown here, and this assembly card is kept inside the enclosure. The enclosure is mounted to the other metal chassis through these 4 bolt holes. The random vibration environment is characterized in terms of a PSD profile shown here. And in terms of the reliability, this PCB with enclosure is tested on a shaker table with given PSD profile for 10 hours. And this PCBA assembly is expected to have a service life of 10 years. And the expected reliability metrics is that within 10 years, we can allow 20% of the assemblies to fail, but not more than 20%. So our objective here is to carry out a random vibration analysis and calculate the life of each of the component solder joints in this assembly and see whether any of the solder joints fail within 10 years, having probability of failure of more than 20%. I'm going to use Ansys Sherlock plus Ansys Mechanical to set up this problem and solve the random vibration analysis. I'm going to also talk little bit about what is the background theory used by Sherlock to calculate the life of each of the components subjected to random vibration excitation. Typically, this is the random vibration results table that we get for every component that is on the PCBA, and we get typical outputs like damage, time to failure, probability of failure, and so on. So I'm going to also demonstrate how Sherlock calculate these numbers from the random vibration strain that is calculated in mechanical. To understand this, we need to have some theoretical background. So Ansys random vibration theory manual, that is part of the Ansys help manual, and vibration analysis for electronic equipment by Steinberg. Okay, this is a very good book if you are into reliability analysis of PCBA. Please refer that. I'm going to refer these two documents to take out some formulas and explain how Sherlock calculate these numbers. For this demonstration purpose, I'm going to use Sherlock 2023 R1, which is released in January 2023. That's the latest version. I'm going to use the tutorial board that is available with Sherlock installation. So once you install Ansys version 2023 R1 inside Sherlock and tutorial folder, there is something called tutorial project. And I have a CAD model of the housing in which this PCB is going to sit inside. So let me start setting up the project. I hope you all know how to open Sherlock. Once you open Sherlock, The first task is to import the ODB archive of the printed circuit board assembly. I'm going to import the tutorial card that is available here. So that is Sherlock tutorial and tutorial card here. ODB++ tutorial stuff. And I'm going to save this in a working directory, and I'm going to give a name, something called this board CCA name is tutorial1. You can give any name. Scan archive and import archive. So now this is going to import the PCBA available inside the ODB archive. Now we can view the PCBs. This is the PCB and there are so many parts inside this. Now I'm going to validate the parts. I'm just going to, all the parts have come in. So some of the parts Sherlock has guessed it as a capacitor that came from ODB++. Now I'm going to check whether these part numbers are available in the Sherlock part library. If they are available, then it will get the appropriate part type and package type. All these guessed information or will be get validated. To do that, I'm going to press Ctrl A, which will select all the parts and select everything. Update from part library. Okay, it has updated all the parts. All these parts are available in Sherlock library. The next task is to set up the random vibration profile. So the profile for us is given here. This is the PSD profile for the random vibration environment. So I'm going to set this up. That is edit profile. This is 20, 80, 80, 350 and 1000. And the PSD values are 0.01, 0.04, 0.07. 0.01, 0.04, 0.04, 0.07. Apply. Sorry, this is 0.007. 0.007. Save. And the duration of this excitation is for 10 hours. We are testing it only once. So we are going to mount this on an electrodynamic shaker and subject to this profile for 10 hours only one cycle. Then the phase, our duration is for 10 years. So I'm setting this as 10 years and number of cycle as 1. And under the reliability goals, the service life is 10 years and our expected reliability metric is 20% of probability of failure. That's been set here. Okay, now let's go back. Layers. So all the parts are there. There are many small resistors, so many small resistors you can see. I know that these resistors are not going to fail. They are very small and strong. So I want to consider only the part which are larger than 10 mm in diameter. So I'm going to hit enter. Okay, only these parts are of my interest. Only I'm going to analyze these parts. Okay. Now I want to demonstrate how Sherlock calculate the life for both leaded components and non-leaded components. For leaded component, I'm going to take this capacitor C23 as an example. For non-leaded, I'm going to take this BGA U10 as an example. Okay. Now let's go to C23. Double click, it will open and set it in a edit mode. Now we can see that the lead modeling is disabled. I want to enable this lead modeling, and I want to say the lead height as 10 mm. Okay. Now you can click on this 3D view button. Once you click on that, it will generate the leads. So this is how the lead look like. Okay. Now we can save this so that we want this to be updated only for C23 part. And also you can look at U10 to filter any part. Just type here U and 10. U10 is basically a BGA package, and we are not going to model the balls here. Okay, for BGA, balls are nothing but the leads, so we are not going to model. I will demonstrate how Sherlock calculate the life for these two parts. Once this is done, now the next task is, since we are going to assemble the PCB inside the casing, this assembly cannot be done inside mechanical. Now we are going to export the PCB assembly as a CAD model into Ansys mechanical. To do that, click on random vibration and say export FEA model. So it will ask you where to export this model. Just take the any location on your machine, preferably a working directory that you have created to handle this project. So just go there and give some name, meaningful name. So it has multiple extensions. So if you want to open this CAD model of the PCBA in Workbench mechanical, your export option should be WBJN format. Select export, and if there is any file, it will overwrite. Make sure display model after export, such that when you say export, it will write out the CAD model of this PCBA in a step format, and also it will generate the Python scripts. That Python script will launch the Workbench and import the CAD model, assign all the material properties for these different parts, and also open that in mechanical. In part modeling, just make sure we are exporting the parts more than 10 mm. And again, in terms of PCB modeling, there are various options how to model the PCB. For now, I'm taking only uniform. I'm not my main objective of this demonstration is to explain how Sherlock calculate the random vibration life. So once we say export here, now what's going to happen is that it is going to export the step file of the CAD model, and it will generate a couple of Python script. This Python script in turn will open the Workbench in the background. That's what is happening here, and set up necessary systems to import this step file, and also will assign the necessary material properties for the PCB and all the components, etc. It's going to take some time to open Workbench and import the model and assign the material properties and open mechanical. You need to wait for a few minutes. After a couple of minutes, the CAD model of the PCBA that is exported from Sherlock has been imported inside mechanical. In the Workbench project page, you will see that the engineering data contains all the material properties for different parts and for leads and so on. And also this system is set for mechanical model of a PCBA is there, and this is also geometry of a PCBA. Just rename that as a PCBA. Now our next task is to make sure these parts are assigned with a these are all the uh, aluminum capacitors, right? And this is a polyester jack, and you can see these are all the ICs, PCBA ICs, and the leads has come in. This is PCB. The next task is to bring in the enclosure for this assembly. So go to component systems, geometry, rename this as a casing, then import the CAD model of the casing here. So I'm going to import the CAD model of the casing. This is a housing here, and open that. Then we need to mesh this housing separately. So take out one mechanical model under the component system and connect to this geometry. So this is a mechanical model of a casing, and open this casing. So it is going to open the casing. This is the casing. The casing is mounted to the other chassis through these 4 bolt holes. You can assign any material for this enclosure. Right now I'm considering this as a default structural steel. Then you can generate the mesh. Make sure the mesh is meaningful. I'm just first generating the default mesh to see whether the mesh size is kind of acceptable. As you can see, the mesh is too coarse. Some of the geometrical profile of the casing is not captured well. This becomes important if you are interested in the stress or life of the casing itself. So I'm going to refine this mesh to 5 mm and see whether it generates a meaningful mesh of acceptable quality. Okay, this is in a meter unit. Let me change this to unit. And another important consideration is that when you are working on Sherlock plus mechanical, you must always work in the unit system, not in the meter or inch unit system. The solver unit system must be in unit system. So this mesh is kind of okay to me, so I'm leaving this as it is. So now let's go and mesh the PCBA. So this is our PCBA. First, make sure your unit system is in and generate the default mesh and see whether they make sense. Okay, so we are generating the mesh. Overall, it kind of looks okay, but there are some issues. If you look at the leads are generated with only one element through the width and thickness. That's not good. We need to have at least 2 elements in the width and thickness direction. And also these chips are having only one element through the thickness, so this may not able to capture the bending correctly. So in order to provide minimum 2 elements through the thickness, I'm going to select this edge, probably this edge, and select by size all the entities smaller than this height. All the entities size smaller than selection. So it's going to select all the entities which are smaller than the selection. Okay, this selects couple of the edges on the PCB on the capacitor outside as well, because let me clear the mesh. These are coming as a separate edges. So what I'm going to do, I'm going to hide all the capacitors now. Hide body. Okay, again I can hide this as well. I don't need this jack as well. So hide body. Then I'm going to select this, select size smaller than selection. Okay, now it has selected all the smaller edges. Then I will also select, I will put this in clipboard. Then I'm going to select all the edges of similar size, so that it will select all the edges on this chip and this chip as well. I'm going to add these lines to the clipboard. Now I'm saying select items in the clipboard, so that it select all the smaller edges. I'm going to give a name selection, or let me straight away insert sizing. I'm going to say number of divisions 2 and say generate mesh. Let's see how it comes out. Okay, you can see that now we are having 2 elements in each direction. Now say show all bodies. Okay, now we kind of got a decent mesh for this. The next task is to assemble both the PCBA and enclosure together. So for that, create a new mechanical model. So here you say PCBA and enclosure. This is just for the naming. So here we need to connect this model and connect this model together, so that we are going to do the assembly. After connecting that, just say update upstream components, so that this is going to remesh this and this as per our setting and get transferred here. Edit this model. As it opens the mechanical, I want to explain another part to you. When you export the model from Sherlock, this is automatically going to open the model in mechanical, and also it will create the name selection for each of the components. When we import the results after performing a random vibration analysis in mechanical, we need to import the result file into Sherlock to calculate the life. During that time, the Sherlock is going to identify all these components based on these name selections. So these name selections are very important. Okay, we cannot change any of these names. The moment we change that, when we import the result file into Sherlock for post processing, Sherlock cannot recognize these components. That is important. Now if you kind of look at this part, it has both the casing and the PCBA inside. I will create some section planes so that we can see the casing inside better. You can see the part. And again, you may have some situations where the PCBA and the enclosure are not aligned properly. If you have any such situation, I would strongly recommend, or you recommend you move the location of the enclosure. You do not move you do not move the location of the PCBA, because when we are importing the results back into Sherlock for post processing, it will look for its orientation. The PCB is identified based on the orientation that we define in Sherlock. If you come back to a Sherlock and if we go to layers, we can see that this crosshair is nothing but the origin. This is the origin of the PCBA. So it will look for the PCB location with respect to this origin. If we kind of move the location or orientation of this board inside mechanical, then when we are importing the result file back into Sherlock, it will not recognize this board. So I repeat again, whenever you want to assemble the enclosure and PCBA, if required, make sure you generate a separate or you go to your CAD system, either Space Climb or whatever you are using. Try to bring these two together, and if at all you need to move only the casing such that it go and sit on the PCB. Do not move the PCB to sit on the casing location. This is very important. Okay, once you are done, let's make a couple of visualization settings so that it will look better. So it has, this geometry has two systems. One comes from PCBA and another comes from the casing. Go back to the details. This one, by default, this is read only. Say this read only to no. Once you set that, it will allow you to change the transparency of the system. Change that to 0.25. Now you can see the PCB sitting inside the casing. So again, if we go back to this one, and it has created many connections between the board and the component here. As you are seeing, this is the contact between the capacitor and the board. Likewise, it has created all the contacts. So you need to kind of go through all these contacts and make sure all the contacts are making sense. It is not defining any contact in non-appropriate places. Okay, that is very important. Manually you have to make sure the contacts are defined appropriately. Okay, now coming back here, now let us, as I mentioned, the name selection is very important. Okay, even in the assembled model, the name selection for all these parts must be correct. So then only Sherlock can properly post process when we take the result file back into Sherlock. But if we look at this, look at what is happening between the original PCB file that is exported from Sherlock and this. The name selection names are changed, right? Component U8, it is saying it is coming from mechanical model PCBA, that is coming from this. So in order to avoid this renaming, just right click and say properties on the assembled system. Here is an option for us. Object renaming based on system name. We don't want this renaming to happen. Just say off, don't rename that. Then come back here and look at that, all those things have gone. So this is the name by which the Sherlock is going to recognize this. Okay, all right. Now there is a contact defined between the board and the casing location. Okay, if this is okay, you can go ahead with this. But now I want to kind of consider a screwing connection between the board and the casing. So for that purpose, I'm going to hide the casing and I'm going to keep only the PCB. I'm going to define the screw connection using beam contacts. So now I don't need this contact region. I'm going to suppress that. Instead, I'm going to create connections, joints, a beam joint. So again, keep your unit system in mm. This is must. Metric ton. Always you should solve the problem in unit system to correctly take the results back into Sherlock. Okay, now I want to apply my reference. My reference body is this. This is my the screw is one side. It is going to connect with this hole, and other side it is going to connect with the whole surface. For that, I'm going to hide this part, and I'm going to hide all the bodies in the group. So one side it is connected to the PCBA, and another side I'm making sure it is going to sit inside this hole. Okay, and this is going to have a radius of 1 mm. So now we can see a new screw type of a connection get created here. So all bodies. So this screw is going to connect this hole and the bottom hole. Clear? So now we did this for one of the screw location. Now we need to do this for 3 more locations. So I'm going to insert beam, 3 more beams, beam and beam. Okay, the second set of bolt holes are here. I will select this and apply, and the third set of bolt holes are here, and the fourth one is here. Okay, so all 4 are defined. By default the other end will come to the origin. So now say show all bodies and hide all the PCBA assembly. Now activate the switching plane. My second bolt hole, the other side is here. So go and select this surfaces. Okay, this is my second bolt, and third bolt is third screw is here, and the last and fourth one is here. So all these screws are of 2 mm diameter, so the radius is 1 mm. Now we can see there are 4 bolt screws like this, and these screws are of aluminum material. Okay, you can change whatever material you have. Now we can say show all bodies. Now remove this selection plane. Now you can see the mesh where it's kind of get assigned. Now I want to create one name selection for the casing. So I'm going to select this material and create a name selection. So if you want to create a name selection for anything that came from Sherlock, give a name called other.casing. So the syntax is that other underscore, after that you can give any name. When you give other underscore, when you import the results inside Sherlock, you can either hide or show all the elements in this others group, other group. Okay, other underscore, here this can be any name. Later I will show you what is the use of this. Just say okay. Now our name selection definition is done. Our mesh is ready, which is coming from the other system. Now we have to set up the new analysis. Before I go further, let me save this project file, save as random vibe enclosure validation. This is done using V20 23 or 1. So I'm saving this file. Okay, to do the random vibration analysis, first we need to do a model analysis followed by a random vibration analysis here. Let me close this property box. So the model analysis result get transferred here. Now go back. So in the model analysis, as we see, our random vibration excitation goes up to 1000 Hz. The typical guideline is that always use a frequency range of 1.5x, meaning that if we are interested to give the forced vibration excitation up to 1000 Hz, go up to 1.5x. 1.5 of 1000 is 1500 Hz. So find all the modes from 0 to 1500 Hz. But how many modes does it exist here? Maybe I expect something around 50, or you can give any number. But it will find out only, let's say for example, there is going to be only 20 modes within 0 to 1500 Hz. It will extract only 20 modes, not all the 50 modes. Okay, that's one thing. Now, the next thing is that when it is going to solve, it is going to generate a large result file. To post-process the results in Sherlock, we may not need the stresses that are coming from the casing, so that we can reduce the file size. Remember that larger the file size of the result file, Sherlock is going to take long time to process that. To calculate the life of the solder joints in the PCBA, I don't need any stresses that is coming out from the casing, so that I can reduce my file size. To do that, go into output controls. We need stress. We may not need strain for Sherlock to process, and if you need calculations, you can keep that. And to instruct Ansys, don't write results for the elements on the casing. We need to use a small command snippet. This command snippet will look like this. I will copy paste here. This is basically coming from outrisk command. There is a command in mechanical APDL solver, outrisk command. This command is going to control what results to be written out in the output file and how frequently we want to write it out. Okay, so what I'm saying now, outrisk erase, it means that it will erase all the setting that comes from Workbench mechanical. Okay, and then outrisk all command none. It means outrisk write stopping all results for no frequency. It means you do not write anything into the result file. Then we are saying outrisk NSYL. NSYL means it's a nodal solutions. Okay, nodal degrees of freedom, like a displacement results for all the modes. Frequency means how frequently we want to write, how many modes we want to write. So we are saying write it for all the frequencies, write the displacement results for the entire model. Then write the stress results for all the modes for the entire model. Then we are saying outrisk, here it will write for the entire model. Here I am saying the stress result, STRS means stress. Okay, so you can see here, STRS, element nodal stresses. STRS, then none. None means for no mode shape. Frequency is none. You do not write anything. For which component? C name, the others, other underscore casing that we have created here. Other underscore case. The name should exactly match. Other underscore case, so that it will not write here. The next job is to set up the random vibration analysis. Before that, we have to provide a support. this is supported at these 4 locations. Now let's say select one edge size, same size, so that it will select all the 8 faces. Only 6 faces selected, some faces are missing. Okay, let's manually select these. Okay, and create a fixed support here. So fixed support, this is chassis. Okay, this is the fixed support for the chassis. Okay, then the random vibration analysis. First thing is insert PSD acceleration. This should act like a base excitation on the fixed support chassis, and direction, it is excited in the vertical direction, so it's going to be G direction. Tabular data, so we have data 20, 80. The tabular data is here, right? 20, 80, 350, 1000, 80, 350 and 1000. Okay, this is 0.01, 0.04, 0.04 and 0.007. Now you see that these 2 lines looking in the green and this line is looking in yellow. It means that the data points that we entered is not good enough to generate an analytical equation for this. In the background, for random vibration analysis, mechanical creates an analytical expression for the PSD curve. This is not good. Usually this happens when we increase the frequency more than one frequency and amplitude more than one order. Okay, look at this. This is e power minus 2, this is e power minus 3. We have created more than one order. In such a situation, it is recommended to provide additional points in this line. Either this is Ansys is using a log interpolation. Okay, either you can provide additional points here manually calculated, or you can click improved fit. Once you click on this improved fit, Ansys will automatically generate additional points in between. Okay, so if you want to learn more about that, go to Ansys help manual and type improved fit. Okay, you can see PSD base excitation, the improved fit. It will explain what is the color coding of green, yellow, red for these graphs. Okay, and another important thing is that we need to set a damping factor. We can set a manual damping factor of 0.04, whatever is the damping factor you have in your analysis, you can do that. And output controls, again, we need to say we need to keep the model analysis results. Sherlock requires model analysis results to post process that. This is a must step. Keep model analysis results, yes. Okay, so once we are done, again use the same command snippet so that we can reduce the stress. Remember that you are solving a small file and you want to look at the stresses on the enclosure as well, then you don't want to use these command snippets. Okay, you can either don't use or you can suppress that so that you can see the stresses on the case as well. Now we can solve this problem. After completing the model solution, let us look at the mode shapes. It has extracted all the modes up to 1500 heads. There is around 20 modes within 1500 heads. Let's look at the mode shapes, evaluate all results. So this is kind of showing because of the true scale, change that to auto scale. This kind of closed with the enclosure. I would expect very low frequency modes on the capacitor leads. Let's kind of cut this one. You can see this is happening on the capacitor. Let me try to modify this slightly. I move the plane a little bit. Yeah, like this. Now come back and see the first mode is just the capacitor vibration mode because of the lead is having a low bending stiffness, and the huge mass is sitting on that. It's bending like a cantilever. And the second mode is the bending mode of the PCB board about the screw points. And the third mode is again the bending mode. So it's kind of the two node bending mode of the plate of the PCBA. It's not only just the PCBA, and also it's kind of a couple mode between the lead bending and the plate PCB bending. Okay. And third mode is again sway mode of the thing. So when it kind of it bends on this direction. And look at the fourth mode. Let's try to this kind of a torsion mode of the PCB. Likewise, sixth mode along the longitudinal two node bending. Seventh mode is the casing mode basically, as you can see. Let me remove the cut plane. You can see the bending. I will try to cut it from other direction. Let me create another section plane here. Section plane. I will cut it here. Now by activating both the things, you can see the bending mode of the casing, and the seventh mode is again the bending mode. Here you can see probably the plate is kind of bending. When it is bending, it should have an effect on the board itself. Let me try to bring this down, bring the amplitude down. As the board bends, it's not only as the casing bends, it is not only the casing. The casing somehow is going to impact the impact the let me try to switch this off. It's going to kind of make the board also experience some vibration. And the eighth mode, again the board bending. And 10th mode, 11th mode, and so on. You can see this is a combined mode between board and both the board component and casing. It's kind of a combined mode, all these things put together. But one interesting point to see here is that our random vibration excitation comes only up to 1000 Hz, up to this mode 907. This mode is 1032. It's little away from the excitation range of frequencies. Okay. All right. Now, having solved that, we see a fair amount of natural frequency within the excitation range. So we must go for a random vibration analysis. Let us set up the random vibration analysis. We have already set it up and we provided some damping, and let's solve this problem, the random vibration analysis. The random vibration analysis should be relatively quick. Once we solve that, we can look at the directional deformation in the G direction, and also we can look at the stresses, equivalent one measure stress in the board. So here you can see the deformation and the equivalent stress. The equivalent stress will be seen only on the PCBA, not on the casing, because we have requested not to write out the stress results on the other case component. But the deformation should be available for the entire board. So if you want to see, just try to minimize that so that you can see the deformation, because we have requested the nodal solution degrees of freedom results on the entire model, not to any specific component name. Okay, all right. Now let us try to understand how the applied PSD value kind of got magnified. First, let me go into response PSD tool, and I'm going to get a response PSD. First point, I'm going to get it on the fixed point location. This is where we applied the input PSD, right? What we want is the acceleration in G direction. This is what we want. We want acceleration in the G values, rather mm square per head square, mm square, per second square whole square by heads. Okay, retrieve this. So this is our applied input PSD. Let me say this is my input, and let us look at our responses at two more locations. Duplicate without results, duplicate without results. The first thing is I'm going to look at on the tip of the capacitor. This is C23, and also let us look at the response on this chip on point. Let me pick, this is U10 response. This is U10 response. Okay, so I'm going to retrieve all the results. So this is how the input PSD is magnified on this stuff. Let us bring all the three charts together, select all the three, and click on this chart button so that you can see all the three charts. It is better, we can visualize this better if we plot it on a log scale. And also right click and show legend. So the red is what we applied as a base excitation, and these two are what we are seeing at those two locations. Okay, all right. Now having done this, these are all equivalent stresses. This is a 1 sigma results and so on. Now we can save this file, and now it's a time to take this result file into Sherlock for live calculation. Right click on solution, open solver file directory. The result file will be available here, file.rst, in this folder. Okay, copy this folder. Now come back to Sherlock. Okay, so before we import the results file, there are a couple of settings we need to do here. One is setting FEA analysis. Sherlock allows to calculate the life of the leads either using the strain or using the nodal force values. By default, it uses the nodal force values from the lead. For this demonstration purpose, I kind of disable, so let it process it by strain rather using the nodal lead forces. If at all you want to use the nodal lead force method, then while we are solving this problem here, we must request for the nodal forces. Not only on the constraint nodes, we must request yes, so that at all the location it will have the nodal forces written into the RST file, so that we can use this approach. Now I am using strain based live calculation rather using the nodal lead based calculation. Okay, apply and close. This setting you must do before importing the RST file. Okay, then come to random vibration analysis, edit properties. Here is the damping ratio. This damping ratio is required to calculate the number of cycles that the PCB and casing is experiencing during the random vibration excitation. I will talk about this a little later. So come to random vibration, edit properties, change this data source from generated to imported. Okay, now here is the place where we need to browse for the RST file that we have generated. Just paste here, hit enter, select file. You will see the RST file that is generated from this random vibration analysis that is available at this location. Okay, this RST file. So once you point to this RST file, select and save and run. You can monitor the progress by going to help task monitor. So here is the place where the import is going on. Once the import is completed, you can see that it is completed. It is showing some 7 errors. It doesn't mean we can't look at the results anymore. Though there is an error, we should be in a process to look at the results. Come back to this random vibe and say view results. Okay, in view results, it is going to show the results for all the components which we have included in the analysis. We have seen these 7 errors, right? Let's look at what these errors mean. Come to issues. Lead modeling is enabled. Random vibration are required for the analysis when lead modeling is enabled. These file must exist in the, okay, let me see. This is looking for this one. Let me see if I have disabled. Oh, I have enabled this. This is wrong. Okay, that's why it is looking for additional files. We must say disabled, then say apply and close. Now we have to re-import this RST file again. Now clear analysis results. This log also we can clear. And now go and edit properties, import that RST file again, save and run results. Now it's again going to re-import the stuff. So this is going to, how much time it is going to take to import the RST file depends on how big the RST file size is. If the file size is really large, it is going to take a lot of time. That's why to make the file size small, we are limiting what results need to be written in the RST file. It is not only depending on the RST file size, it also depends on how many components present in the model and how large the mesh is. All those things play a role. Okay, now there is one analysis error, view results. Now we can see part validation is not completed. This is okay, this is just the warning, this is not the error. Now we can come to a random vibe tab. Here is where we are going to see the results for individual components. Here we will see the part strain and the lead strain. In this tab we will see the lead strain. We have modeled the lead only for C23. There are 2 stuff. Now let us look at how these strains are calculated, okay, for lead and other thing. So this strain is basically coming from the stresses that is calculated here. Okay, now let's say for example, if you look at these lead as elements, these leads have elements, and these strains are coming from the stresses that is calculated here. If you want to really understand how the stresses that are shown in the mechanical is converted into this number that you are seeing here, lead strain, then there is another YouTube video that I have created. Go here, type for Sherlock strain calculation. Go to YouTube and search for Sherlock strain calculation. So you will see another video here. Sherlock strain calculation for part and PCB in the random vibration analysis. If you kind of watch this video, you will understand how the strain that is calculated in the mechanical is transformed into all the Sherlock stuff. Okay, I hope you will watch this and understand the meaning of the pod strain, PCB strain, lead strain, and so on. Okay, now let's come back to this. So we want to look at two results. First, U10 is one that is of our interest. The U10 is experiencing a strain of 453. Okay, how is this 453 coming? This 453 corresponds to 1.95 sigma results. If we go back to Ansys help documentation, there is a theory guide, okay, Sherlock theory guide. Under that, random vibration theory guide, if you kind of come here to the section 5.4, this will talk about how the strain is calculated for random vibration analysis. This corresponds to 1.95. Why 1.95? As I was telling, two references. One is the Steinberg book is a good reference if you are doing any vibration analysis of PCBA. There is a dedicated chapter 9 for random vibration analysis. So if you kind of go down to page number 213, you will see usually this kind of follows a 3 sigma rules to calculate the life, considering 1 sigma, 2 sigma, and 3 sigma. That's called a 3-band technique. But for electronics enclosure, Steinberg suggested a simplified approach. Instead of using the 3-band techniques of taking 1 sigma, 2 sigma, 3 sigma strains and calculating the damage due to all these three, he proposed a simple approach. I will go back there. 213. So this is the 3 sigma approach. Instead of that, he proposed another method where he says, instead of where is that? Yeah, by doing a equivalence for approximate random vibration fatigue, we can use something called 1.95 sigma. Okay, so Sherlock is following this 1.95 sigma to calculate the strains that is given here. Okay, again, remember that I'm not really going deep into teaching the random vibration analysis. I'm just pointing out what Sherlock is doing. Okay, it is using 1.95 sigma. Why 1.95 sigma? It is coming from Steinberg's books. Okay, now having that, it is having a strain of this much. Now let's go back to the theory manual again. If we go back to Sherlock theory manual 5.4, let's look at what's the formula is being used for lead less. When the leads are disabled, this is the formula it is going to use to calculate the number of cycles to failure. Let's I will just open up an Excel that I already prepared, but I'm going to redo this for this particular strain value. Okay, let's first start with U10 with no leads. You know that service life is 10 years. That's what we have input as a life cycle. Service life is 10 years and reliability matrix is 20% of probability of failure. Now, so to do this, this is the formula. In this formula, first thing we need to do is we need to, when this is when with leads. Now let's go when there is no leads. When there is no leads, first thing is we need to calculate NC. NC is nothing but a reference number of cycles for failure. This is taken as 20 million. Again, this 20 million is coming from the Steinberg book. If you go to page number 216, I believe, 215, 216, so it says that the component is expected to achieve fatigue life of 20 million stress reversals, okay, in the random vibration environment. So we are keeping this as a reference, 20 million. Then EC is the component critical strain value. The component critical strain value is calculated based on this formula. This formula contains two parameters. One is zeta, that's the board level strain value, and another one is C, that is C is a correction factor, and L is the diagonal length. This L must be in inch unit. The L is calculated as a diagonal length. For example, let me show you how this is calculated for U10. Go to part list and go to U10, and this is BGA part, and this package has a package length of 27 mm in the width and length direction 27 mm, right? So I'm going to put the width as 27 and length as 27, and the diagonal is calculated as square root of x square plus y square, okay? This is in mm. We need to convert this into a inch such that we will get this factor L, diagonal length. Then the zeta, this zeta, as I explained here, this zeta is calculated based on the solder material. Where is zeta explained? Yeah, this zeta is calculated, represent the analogous. It is displayed in Sherlock solder library critical strain life value. Okay, now let's go back here. Let's understand what is the solder material being used here. This should already show. Okay, this is using 63 SN and 73 PB. Now let's go back here to Sherlock and library solder material. So 63 SN 737 PB, high cycle modulus, and this is the critical strain value. Okay, so I'm using critical strain value coming from this 3.75 e power minus 4. Okay, then the another factor is called the correction factor, that is nothing but this C. Again, the C is given based on different package type. If it is a DIP, if it is a pin grid array, LCC component, and BGA, and so on. Okay, this data is available also in Sherlock under solder material, solder fatigue, library solder, go to the solder type and go to correction factors. So you can see for BGA, U10 is a BGA, Sherlock is using BGA correction factor of 2, whereas Steinberg is giving 1.75. But however, this 2 is given based on the experience that Ansys has obtained by doing so many testing over many years of that. But however, user has a flexibility to go and modify this number based on your own experiences that you have seen in your labs. Okay, this is how the C factor is coming in. So I have a C factor of 2 for BGA. Now we can use this formula. We know zeta, we know C and square root of L, and we can calculate what is the strain here. That is going to be EC. EC is nothing but zeta by C square root of L. Okay. Now let's take strain from FEA. The strain from FEA for this component is 543.93. 543.93. Let me update this. 543.93. So this is in a micro strain. I'm converting that into a absolute strain by dividing it by 1 e power 6. Micro strain to strain. Okay. So NC is 20 e power 6, and we can calculate this EC. And B is a material constant. This B, again, this is available under solder profile. Let's go and I will just show you library solder. And this one, and high cycle fatigue, the FEA power is nothing but the B, 6.4 for this solder. So I'm going to use 6.4. Now we can substitute NC, all these formula here. Now we are going to get the NFEA, that is nothing but cycles to failure. Okay, we got 5.95 e power minus 3. Then there is some more calculation we need to do here. One is that the duration is 10 hours. Then this 10 hour corresponds to 36,000 seconds. Okay. The next step is to calculate the zero crossing frequency. In case of a harmonic excitation, at any given point of time, there is only one frequency is exciting the structure. So we know what is the frequency at which the structure is vibrating. But in case of a random vibration analysis, at any given point of time, more than one frequency is exciting the structure. Okay, so we don't know at what frequency the structure is vibrating. To calculate the number of reversals, we use some concept called zero crossing frequencies. The zero crossing frequency calculation is explained in Sherlock. Let me show you that in Steinberg book. So it uses this particular formula to calculate the zero crossing frequency. The same is also explained in Ansys help manual. I will let me see. I don't know why it's not showing up. Okay. Anyway, let me explain from the images that I have. So the zero crossing frequency is calculated based on this formula. This formula itself is coming from Steinberg book. Okay, page number 232. That's what it is coming in. So here, first of all, this is nothing but summation of the PSD values at all the natural frequencies. F1, F2 are all nothing but the natural frequencies. If we look at this particular problem, so we have many natural frequencies. Let's identify what are those. Natural frequency. These are all the natural frequency up to 1000 Hertz we have to take. Okay, that is up to here. So I'm going to put these natural frequencies here. So we had 11 11 natural frequencies within that range. Sorry. Yeah. I think, is there one frequency exactly at 350? Just kind of make sure. Yeah, there is one at 350 as well. Okay, good. So now we are having that. This is my input PSD profile. This is going to use a log interpolation. Okay, so now the question is that we have a input PSD something like this. Now we need to know at 74.48 hertz what is the input PSD value. This PI is nothing but the input PSD value. Okay, so we need to know that. To do that, we have to use a log-log interpolation. I'm going to explain here how to do the log-log interpolation. This is my natural frequencies. So I have my first frequency at 80 hertz. Just want to going to reconstruct the whole thing. And another one I have it at 80 hertz. Let me use 80 hertz here, and 350, and finally 1000. So these are all the frequencies I have. Let me delete these. I'm going to put these values. Let me copy this, and okay, let me delete this one. Okay, now let's see how this is going to work. 20. Okay, I'm going to do a log-log interpolation. I'm not really getting into the details of the log-log interpolation, but this is the whole crux of it. Okay, so here the last point is somewhere you will give a problem. So we will put 1000 here so that we are going to get, for the last point we don't need. Let's see what's happening. To do the log-log interpolation, I need to provide starting frequency and ending frequency. Okay, so I have developed interpolation algorithm that will do the interpolation based on this. But important point you need to remember is that the interpolation is based on the log-log algorithm. So once we do that, initially we had only these 4 points. Now we can see more points, one coming at 74 point, and all these natural frequencies, now we have the value. Now to calculate the zero crossing frequencies, we can reference this formula here. Only pi is coming from this lookup table. Okay, so it will look for 74.418. What is the value here? That is 37037 stuff. So that will come in here, 037 and so on. So I'm just coding this. All the natural frequencies within 1000 hertz. Then this is the omega is nothing but 2 pi f, and this qi is nothing but 1 by 2 zeta. Again, that is coming from Steinberg book, page number 34. Here the zeta is the modal damping ratio I was talking earlier. Here you can input these values, random white, edit properties, generated. So here if you have multiple modes, let's say for first mode you want to give 0.5, for second mode you want to give 0.03 percentage, for the third mode you want to give 2.5, something like this. For every mode you can specify the individual GI. In this case I'm assuming all the modes are having the constant 0.01 damping. Again, remember that if you are changing this value, you have to save this. Don't hit save and run. Save this value. Again, you have to re-import the RST file. Going back here, edit, imported, and import the RST file. Then only that zeta value will be taken into account. Okay, all right. Now I'm using zeta of 0.01 for all the modes. This is zeta. Then delta F is calculated by Fi by Qi. Fi is the natural frequency and Q is here. Next comes P. P is coming from the log-log interpolation. Then we are going to use this formula, whatever is here, and we get our, then we compute for all these values. Finally, we will sum the numerator term and we will sum the denominator term, and ratio of those two is nothing but the zero crossing frequency. This zero crossing frequency is um, available in Sherlock. Here we edited something. I'm going to re-import this. This is going to take some time. Let us see where Sherlock is reporting that zero crossing frequency. So every time you make any changes in the analysis setting, we need to re-import that. Okay, view results, leads. In the summary, you can see 106.83. We are seeing here 107.9. This may be due to small round off, but this is how it is happening. This is correctly implemented in Sherlock version 2023 R1. There was an issue with Sherlock 2022 R2. In implementing this formula, here this delta F is F by Q, right? There was an issue in the code. The F is not correctly coded. The delta F term has become kind of 1 by Q instead of Fi by Q. That issue is corrected in 2023 R1. And also another difference between 2022 R2 and 2023 R1 is that the QI is computed using 1 by 2 zeta I. In 2020 R2, it was computed using a different formula. It was computed using this formula. This again comes from Steinberg reference, but still we have done some modification of what comes from Sherlock. Say for example, if we go to 235, the Steinberg says Q is equal to square root of Fn, right? So this is nothing but, let me explain. Q equal to square root of Fn Fi. This is nothing but Fi power 1 by 2, right? This is what it is. Now, when we, instead of using this, usually the model damping ratio kind of reduces as we go on higher modes or at the higher frequencies. As we go on higher mode number or frequency, the damping ratio typically reduces. So what Sherlock implements, that instead of using just 1 by 2, it uses something like this: 1 plus n plus 1. This n is nothing but the mode number. So what it means in the sense, for first mode number, this becomes 1 by 2. This is same as what is given in Sherlock. But for the second mode number, this will becomes 1 by 3. So this value will be little lower than that. For next mode, it will become 1 by 4. So that it is trying to capture a kind of a decreasing order. But still, this is kind of debatable whether this is correct or not. That is the reason in version 2023 R1, we have provided option to the user. Okay, so what damping ratio should be used here, rather we kind of assuming some value. Okay, that is another difference between 2023 R1 and 2022 R2. Okay, all right. So this is how we compute zero crossing frequency. Coming back to this life calculation. So for this problem, the zero crossing frequency as computed by Sherlock is 106.83. So I will use this value, 106.83. Now we can calculate. So now the structure is vibrating at 106 hertz for 36,000 cycles. That means it totally completes these many cycles. Now we can calculate damage per cycle. This is cycles to failure is nothing but what we calculated using this formula. Now damage per cycle is nothing but 1 by CTF. Then this is the damage per cycle. Then we can calculate what is the total damage for these many cycles. Okay. So once we calculate that, then we can calculate time to failure. Time to failure is nothing but service life divided by total damage. That is kind of documented. TTF, total time to failure, is nothing but service life divided by total damage. So now we are seeing a TTF of 0.15015. Let's look at what is coming here. Okay, this is rounded off to 0. Let us try to export this table so that we might get some more closer accuracy of result. Let's see. I haven't really tried. Let's see. Okay, let's go back here. Live table, open, U10. Yeah. So here you can see, because the Sherlock output window rounds off this to kind of one decimal. Okay, so here you can see 0.01546. That's what we are seeing here. 0.01546. Okay, then the beta. What this means is, now we can also see the life curve for this component. View life prediction. This is the stuff. It means that probability of failure is 100%. This means that we are expecting this component to survive for 10 years with 20% probability of failure, but this component is going to fail in 0.015 year itself. This is where it's going to fail. Okay, this is really not good. That's what this is showing. But to plot this curve, we need to have a Webull function. I'm not really okay. Now let us look at some other curve so that you will understand better. See, now if you look at this component U16, this is kind of going to pause here. So we are expecting this to kind of work as expected for 10 years, and the probability of failure is just around 4%. So this is kind of meeting our requirement. But how do we generate this curve? I will show you the curve something like this. So how do you interpret this curve? This part is going to meet the reliability goal of 20% in the total population in somewhere around this time. 20% failure will happen just after 4 years. All the 20% of the total population would have failed instead of failing after 10 years. That's the way you understand this. Now this curve shape depends on Webull parameter called beta. So by default, Sherlock uses beta of 3. But however, based on your field failure data, if you have, you can always go and modify this beta value in here. Go to the solder material, low cycle fatigue, Weeble beta for BG. By default it is 3, but you can modify different beta value for different components. I was also talking about this correction factor. Not all the possible package types are listed here. For any of the package, the correction factor is not listed here, then Sherlock is going to use default value of 1.0 as the correction factor. Okay, but for the part type which are listed here, you can change this value. And also I mentioned where it is coming from in a Steinberg book. Okay, now again, the total damage reported by Sherlock. Let me take this Excel file. Total damage is this much. Not this. I think I have to use this. Total damage is this much. This is closely matching with what we have hand calculated, right? This is what Sherlock has reported. And TTF reported by Sherlock is this, and our hand calculated value is this. They are kind of matching, right? They are matching well. And probability of failure, 100% it is showing. Hand calculated, the Sherlock is also showing 100% probability of failure for beta of 3. Okay, so if you look at the percentage difference, there is less than 0.01% difference. I hope this gives you an idea about how Sherlock calculate the TTF and the total damage and so on for non-leaded components. Now let's look at an example for leaded component. Leaded component, let's take C23. Let me go back here. C23. Okay, again going back to documentation for component with, when leads are enabled, it is going to use a different formula. That formula is here. I will switch this now. When leads are present, it's going to use different formula. Okay, so this require the element equivalent strain. The element equivalent strain for C23 is here. C23 486.93. 486.93. Okay, then EF, this is the fatigue coefficient for the solder ball or the lead material. Again, this value is in the material library. Say for example, we will go back here. The lead is made up of a copper. Okay, so we will go back to material and search for copper, and copper high cycle fatigue, and it is having two values here, right? So one is the EF, this is 3.2 e power minus 3, and another one is factor B, that is fatigue exponent, that is here for the lead material, that is copper in this case. So now we have all the values. E is the strain on the lead due to the random vibration excitation, that is calculated by mechanical and transformed to Sherlock at 1.95 sigma. The exact calculation procedure is explained in this video. Okay, Sherlock strain calculation for part and PCB random vibration analysis. And also you can learn that from the theory manual. Somewhere it explains how it is actually calculated. If you go here, yeah, this will explain how the lead strain, lead pot strain, lead PCB strains are calculated. Okay, the same thing is explained in that YouTube video for your reference. Okay, all right, let's come back here. So we have 486 microstrain. We know what is the EF and EB, and if we substitute in this formula, we are going to get cycles to failure. This is very huge. Okay, e power 9. And duration is 10 hours, and zero crossing frequency is same as this, and it's going to withstand the same number of cycles. Then the cycles to failure is this much, and damage per cycle is very low. Total damage is again very low. The TTF is 4000 something. Let's look at what we got it from Sherlock. This is U23 is here. TTF is 4187. You see, this is a huge number. Okay, we are not bothered about small decimals, right? TTF is 4187. But if you look at in this table, this is just going to show more than 100 years. Okay, because it doesn't make sense when electronic component survive more than 100 years. So usually when the number is very large, that's capped off to the closest meaningful number. Though it is showing here as more than 100 years, but if you want to really look at the thing, export this as a table, as I did, then you can see 4187. Then let's look at damage. This is 2.388. Where is that damage? You can see that 2.388 is what is coming as a damage calculated by Sherlock. Let me make it here so that you can compare. This is the total damage is this much, and the TTF is this much, and the probability of failure is this much. Okay, the hand calculated values, the probability of failure is going to be very low, so we are not really bothered about this. Okay, so POF made it in the percentage, rather in the percentage. Let me make scientific. Okay, this P of when the damage is very small, it doesn't make sense. No need to compare. But overall, you can see that TTF hand calculation and calculated by Sherlock is closely. Oh, okay, this is again going to be a percentage. Format number, and okay, let me make this as a percentage. This is a percentage. Format cells, percentage. Yeah, in terms of a percentage, it is displaying is very difficult. But let me make this as percentage. I will multiply by 100 so that this are in percentage. Okay, what Sherlock reports as a POF is not the absolute number, it is a percentage. Okay, that you need to understand here. The probability of failure is 100, means 100% failure. I hope this explains how Sherlock calculate the reliability measures like total damage, probability of failure, TTF from the mechanical random vibration analysis. Okay. I kind of summarize again. So our original objective was to calculate the probability of failure or the reliability assessment of a PCBA, which is inside an enclosure subjected to random vibration analysis. I have taken you through a step-by-step procedure of importing the ECAD file into Sherlock, then exporting that into mechanical, Workbench mechanical, then how do we mesh the PCBA in Workbench mechanical, and also we discussed about how do we bring the casing model inside Workbench, how do we mesh the casing, and then how do we connect the casing and PCBA together. And also I explained the importance of running the analysis in unit system, and also the importance of creating the name selection, controlling the file size, and so on. Then first we did a model analysis. In the model analysis, we tried identifying the vibration modes of the individual parts and the vibration modes of the PCBA and the combined PCBA plus casing vibration modes. And also we can understand the stress distribution inside the PCBA. I have referenced to another video to understand how the strains reported for each part in Sherlock is calculated from mechanical results. Then we also looked at how to interpret the life curve using Weibull distribution, and using these two references, Sherlock Random Vibration Theory Manual and Steinberg book on vibration analysis of electronic equipment, we have seen how the damage, TTF, and the probability of failure values are calculated by Sherlock. And through an Excel sheet, we manually calculated the damage, TTF, and probability of failure, and shown that the values are matching well with that of a Sherlock calculation. And also I have highlighted about how do we calculate the zero crossing frequencies, log interpolation of the PSD spectrum, and some differences between version 2022 R2 and 2023 R1. Okay, usually 2022 R2 calculates zero crossing frequency as a lower number. When this number is lower, what it means is the number of applied cycle will be less. It means the damage value that we are calculating is less compared to the actual values. It means V2020 R2, if you are using, you are slightly under conservative. Okay, you are calculating a less damage compared to the actual formula, but that difference is not very much large. But if you are at the border, this may become important. So make sure you use the appropriate version of Sherlock when you are doing the analysis, depending on how much margin you have. You have a lot of margins, then this difference doesn't not really important to you. But if you are very close to hitting your reliability targets, then I would recommend you to double check on this. Okay, I think I have covered all the parts that I wanted to explain. So this demonstration help you to understand how Ansys Sherlock plus Ansys Mechanical help to predict the reliability assessment of electronic component based on physics of failure analysis, because here all the strain values that we are using is based on the actual physics. It's not from any handbook based MTBF calculation. Hope this helps. Thank you. Bye.